So we've seen that this definition of limit does not call upon the infinite, which is a good thing. We like that. Two drawbacks. You can't use the definition to determine what the limit is. You need to have a candidate for the limit. And then you plug it into the definition to see if it is indeed the limit. So you can verify that a given value is the limit. That's good, but you can't use it to find the limit. That's an annoyance. And the other thing is that it's a little bit artificial, right? I mean, you have to sort of play around with the absolute values and the inequalities in order to find the right n epsilon. But that's just the nature of analysis. So practice will get you to the point where you can find the integer n epsilon, the threshold that's required in order for the definition to hold. Don't despair. This is something that you learn how to do with practice. Here's one thing you can say though about limits of sequences. They are unique. If a sequence does converge, it only converges to one value. And how we're going to prove that? We prove it the way we usually prove uniqueness in analysis. We're going to suppose that there are two limits, and we'll show that the only way that this can make sense if both limits are actually the same. So we'll assume that the sequence xn converges to x, and that it also converges x prime. According to the definition, if epsilon is greater than 0, then epsilon over 2 is greater than 0. Now, epsilon over 2 is a positive quantity, and so, given that xn converges to x and to x prime, you can find an n epsilon over 2, so it's an integer n which depends on this positive quantity, and another integer n prime epsilon over 2, such that xn minus x is less than epsilon over 2 when n is greater than n epsilon over 2. We're talking about convergence to the first limit. Xn minus x prime is smaller than epsilon over 2 when n is greater than n prime epsilon over 2. Convergence to the second limit. Set n epsilon to be the greatest of either n epsilon over 2 or n epsilon over 2 prime. What this means is that if n is greater than n epsilon, it will be simultaneously greater than n epsilon over 2 and n prime epsilon over 2. Picking the maximum of those is our way to make sure that we have one threshold which satisfies both at the same time. Then, when n is greater than epsilon, both of these are satisfied. Let me write it this way. We know that x minus x prime in absolute value has to be greater than or equal to 0. Now we're going to rewrite the absolute value here as such. We use the trick that we very often use. Add 0, we write 0 in a way that will allow us to use the triangle inequality. Due to the properties of the absolute value, this is the same as saying n minus x in absolute value, xn minus x prime in absolute value. Now, whenever n is greater than n epsilon, xn minus x is smaller than epsilon over 2, because in particular n is also greater than n epsilon over 2, and when n is greater than n epsilon, n is greater than n epsilon over 2 prime, so this second term here is also smaller than epsilon over 2. We get this quantity, x minus x prime, in absolute value, can be made smaller than any positive quantity. Well, there's only one way this can happen. It is if x minus x prime in absolute value is equal to 0, which is to say x is equal to x prime. And that completes the proof. I'd like to make a remark here in terms of how we're going to write things down in general. We won't usually add this little bit, but we won't usually specify the epsilon over 2 here. We'll just say, if you give me any positive quantity epsilon, I can find two thresholds, n epsilon and n epsilon prime, such that xn minus x can be made small enough. And small enough will mean epsilon over 2. Now, the epsilon which is here is the same as the epsilon which is here, but I'm not interested in this being smaller than epsilon. I'm interested in it being smaller than epsilon over 2. We get rid of this guy. We would have similarly that xn minus x prime in absolute value would be smaller than epsilon over 2. That makes sense. Whenever n is greater than this one, and then we would say this new n, we call it n epsilon star. Then whenever n is greater than n epsilon star, I get this. Okay, so this is usually how we're going to write it. But if you're not feeling comfortable with this, there's nothing to stop you from going back to specifying epsilon over 2 in positive and then really working with these quantities. It's the same argument. Another thing that you might say is to say, look, my definition says nothing about epsilons over 2. It just talks about epsilon. Let me try to be strict about this. Let epsilon be greater than 0, then I can find an n epsilon and an n epsilon here as well, such that xn minus x is smaller than epsilon. Whenever n is greater than n epsilon, and xn minus x prime is smaller than epsilon when n is larger than n epsilon prime. And so I'm going to set n epsilon star to be the maximum of the two thresholds that I have. And then whenever n is greater than this maximum, then everything else stays exactly the same, except here we would end up with x minus x prime in absolute value being smaller than 2 epsilon. Well, the only way that this can be true for every epsilon, because epsilon is arbitrary, is if x minus x prime in absolute value is equal to 0, just to say that x is equal to x prime. So we're gonna basically go back and forth between these three ways of working the epsilon and n epsilon arguments. Later on, we'll talk about epsilon delta proofs. We'll talk about limits of functions. Differentiability will be the same idea. The key point is that I can find a point in the sequence after which the difference between the terms of the sequence and the limit is small enough. Quantify what I mean by small enough using my epsilons and my multiples of epsilon. You can end up with epsilon square here. It will also give you the same sort of reasoning. We'll say that a sequence of real numbers is bounded if you can find some positive number m such that the absolute value of every term is smaller than m. Of course, here the sequence is the sequence xm. Now we have a nice theorem about this. Convergent sequences are bounded. If you use your intuition, that makes sense, right? In order for a sequence to be convergent, eventually all of the points have to fall in the neighborhood. Well, the epsilon neighborhood is bounded, right? It's I think that might be distance to epsilon, and all of the points are in there except for potentially a finite number of points. And then each of these points being a real number is also bounded. There's some constant which would be larger than all of them. So you would expect the convergent sequence to be bounded. Whereas the one example of a sequence which is not convergent, the sequence 1, 2, 3, 4, 5, 6, 7, and so forth, diverged and was unbounded. Now there are divergent sequences that are bounded. So this statement here is not an if and only if statement. All we say is that if a sequence is convergent, it has to be bounded. If all you know of a sequence is that it's bounded, you can't conclude that it's convergent. Let's assume here that this sequence xn converges to x. We'll pick a specific value of epsilon, the value 1, which is larger than 0. You'll agree with it. Now, by definition of the limit, for every epsilon, we can find a threshold after which all of the points in the sequence are within epsilon from the limit. In particular, this is true if epsilon is equal to 1. You can find an integer n such that xn minus x is smaller than 1 whenever n is greater than n. In particular, using one of the properties of the absolute values, what you get here is that the absolute value of xn minus the absolute value of x is smaller than the absolute value of xn minus x, which is smaller than 1 whenever n is greater than n1. And so xn is going to be less than absolute value of x plus 1 here in absolute value whenever n is greater than 1. So now set m to be the maximum of this value here, and the absolute value of all the terms that came before the term n1 plus 1. So all the terms up to n1. So what we have is that from n1 onwards, so n1 plus 1, n1 plus 2, n1 plus 3, and so forth, each of the term here is smaller than x plus 1, and then all of these other terms, well, they might be larger than the absolute value of x plus 1, but if we set that to be the maximum, let's just add 1 here to be on the safe side so that we can have strict inequality. And this number is going to be greater than 0 for sure, because this number here is greater than 1, so it's greater than 0. And every term of the sequence, not just those greater than n1, but all of them have to be smaller than m in absolute value, which concludes what we wanted to show. The sequence is bounded. I want to formalize what I said about if and only if statements, just in case you don't fully remember these things. When you have a theorem or a result, typically they are of the form if A, then B. The contrapositive of this statement, if not B, then not A. So the contrapositive of the previous statement that says if a sequence is convergent, then it is bounded, would be if a sequence is unbounded, then it is not convergent. And that statement, the contrapositive, always has the same truth value as the original statement. So what we have is that A implies B as a statement is equivalent to not B implies not A. Sometimes it is easier to show A implies B by showing not B implies not A. There's something else that you can build that looks like A implies B. It is the converse. The converse statement would be B implies A. And in general, A implies B is not equivalent to B implies A. With the bounded convergent sequence example, the converse would be any bounded sequence is convergent. That's not the case. For example, the sequence minus 1 to the n is bounded by 2. So minus 1 to the n is always smaller than 2 for every n, but if you look at the sequence, this would be minus 1, 1, minus 1, 1, minus 1, 1. It doesn't converge to any value. It's bounded and not convergent. Statements for which A implies B is equivalent to B implies A are if and only if statements. That's not saying the same thing. If and only if statements, you are literally saying that a statement is true and that the converse is also true. So you have to be on the lookout for these things. A lot of the proofs that we will do in this class will rely on us recognizing this rule from logic, and as well, whenever we do prove if and only if statements, we typically have to prove two things. one direction and the other direction.